Hello everyone, my name is Mohammad Shakib and I am from Sri Venkateshwara College of Engineering. Today's topic is the Hall coefficient. Hall's coefficient, understanding the essential of electrical conduction. Hall's coefficient is a fundamental parameter that provides invaluable insights into the nature of electrical conduction in a material. It serves as a powerful tool for studying the underlying charger carrier properties, shedding light on the interactives of electron and hole dynamics. Electrical conduction in metals. Free electron model, charge carrier density, electron mobility. First of all, free electron model. In metals, the conduction of electricity is primarily driven by the movement of free electrons, which are not bound to individual atoms but can freely move throughout the material. The density of charge carriers, which can be electrons or holes, is a crucial in determining the electrical properties of a material. Electron mobility. The mobility of charge carriers, which reflect their ease of movement, also plays a significant role in the overall electrical conductivity of a metal. Lorentz force and Hall effect. Lorentz force. When a current carrying conductor is placed in a magnetic field, the moving charge carriers experience a transverse force known as Lorentz force. Hall effect. The Lorentz force also causes the charge carriers to accumulate on the side of conductor, creating a potential difference known as Hall voltage. Hall coefficient. The Hall coefficient is a measure of the potential difference and provides valuable information about the charge carrier properties of the material. Derivation of Hall's coefficient. Charge carrier density. The starting point is the relationship between current density, charge carrier density, and charge carrier velocity. Hall voltage. The expression for the Hall voltage is then derived, leading to the final equation for the Hall coefficient. Lorentz force. The Lorentz force experienced by the charge carriers in the presence of a magnetic field is then incorporated into the analysis. Assumptions and significations. Uniform current distribution. The derivation assumes in a uniform current distribution throughout the conductor. Single carrier type. It also assumes that the material has only one and only one type of charge carrier, either electrons or holes. Negligible scattering. The analysis considers the case where charge carriers scattering is negligible. Steady state conditions. The derivation is based on steady state conditions where the system has reached equilibrium. Calculation of charge carrier density. Hall voltage. The measure Hall voltage combined with the applied magnetic field and current can be used to calculate the charge carrier density. Hall coefficient. The Hall coefficient, which is the ratio of the Hall voltage to the product of the current and magnetic field, is a direct indicator of the charge carrier density, electron or hole density. Depending on the sign of the Hall coefficient, the coefficient, the charge carrier density can be attributed to either electrons or holes. Material characterization. Determining the charge carrier density is a crucial for understanding the electrical properties and performance of the material. Calculation of charge carrier mobility. First of all, charge carrier density. The charge carrier density, as determined from the Hall effect, is a key parameter in the calculation of mobility. Electrical conductivity. The electrical conductivity of the material, which can be measured independently, is also required for the mobility calculation. Hall coefficient. The Hall coefficient, which reflects the charge carrier properties, is the central piece of information for the mobility calculation. Interpretation of Hall coefficient. Sign of Hall coefficient. The sign of Hall coefficient indicates the dominant type of charge carrier, either electron or holes. Magnitude of Hall coefficient. The magnitude of Hall coefficient provides information about the charge carrier density of the mobility in the material. Material characterization. A Hall coefficient is a powerful tool for studying the electronic structure of the transport properties of materials. Applications. The insight gained from Hall coefficient are crucial for the design and optimization of electronic devices and materials. Conclusion and applications. Let us see the conclusion and application part. Fundamental understanding. Hall's coefficient provides a fundamental understanding of the charge carrier properties in materials, enables deeper insights to electrical conduction. Material characterization. The measurement and analysis of Hall coefficient is versatile tool for the characterizing the electronic structure and transport behavior of materials. Device applications. The knowledge gained from Hall coefficient is crucial for the design and optimization of electronic devices such as sensors, transistors,